Hello friends, welcome back to the bench. Thank you very much for joining me. Our patient is a b2600 Mazda, which actually it has been sent here before for a rebuild, right? You see how nice and shiny it is, right? Super clean, all new cabs, all the corrosion and stuff like that removed. However, this one didn't actually have much damage from corrosion, right? Everything here looks pretty good, right? I don't actually remember. I could review the footage, but it's not that crucial what it looked like. But I'm pretty sure the cap was just really in the really bad condition, and that was pretty much it, right? So we just replaced two caps. We replaced the film caps and stuff what we usually do on these. Typically, when the customer sends this for a rebuild, I don't really get any information regarding what's wrong with it, right? It just, we just purchase via eBay, and you send it in. I do my magic, and I send it back. But in some cases, I ship it back, and there are some issues, and this is one of these. So what we know from the mechanic is that we have no injection. However, the mechanic said that injector number 1 is working and all the rest are not working, which is kind of puzzling because we have two injection lines on this one. These two caps sitting on two injection lines, and these two transistors are actually controlling the injection, right? So usually if there is a problem with the injection, it's usually number 1 and 3 doesn't work, or number 2 and 4, and I'm actually not sure how they are connected. It could be maybe 1 and 4 and 2 and 3. It doesn't really make much difference, but you want to see 2 of them not working or 4 of them not working. 3 of them not working, that could be something else. That doesn't necessarily have to be an ECM issue. They also said that it has weak ignition. And we got someone revving the engine outside. And what are you gonna do? So first, let's focus on the injection, because that is the main issue, and then we're gonna check the ignition. So first, let's switch to resistance, and let's do the range of 5K and high speed, right? So we can quickly test. So now what we want to do, first we're going to catch a ground on the other side of the board, so anywhere on the other side of the board. So let's maybe catch this one or this one over here. Then what we want to confirm is first that the emitters of the injector or of the injection transistors are sitting on the ground, because this is ground controlled, so we want to see these ones sitting on the ground. We have 400 milliamps, so that's the resistance of the probes, resistance of the board. This is fine. And these two, the same way, right? About 400 milliamps. So we are sitting on the ground, that's good. Now we want to check the collectors. So the collectors should be roughly open, especially at 5K. They should have like mega ohms. So in this case, we're gonna have open overload or open line, however you want to interpret OL. Okay, and the second collector is also open. Perfect. So now the bases. So the base on one of these should be 570 ohms. This should probably be fine. It seems a little low, but it should be fine. And the other one, we have a dead short to ground, 400 milliohms. So this transistor has shorted base. Now this is not a good news by no means. Because it's either the transistor that is shorted, and here's the difference between the regular bipolar transistor and a MOSFET. If you see this on the MOSFET, that the gate is shorted to drain or to source, then usually that means that also the source and drain are also going to be shorted. So the whole transistor is a piece of wire, essentially. Which means that whatever the drain was supplied with, whatever voltage, that voltage went to the gate, so it went to the control logic. So be it an MCU, in this case MCU is controlling that. Which means you're gonna have a bad day. In bipolar transistors, on the other hand, the base is in between the collector and emitter, right? It's kind of like a more complex diode or a controlled diode. So it is very possible that the gate, not the gate, the base, is shorted to the emitter, and this transistor is the only problem here. Let's hope it is, because if we remove the transistor and we still have the short on the base, that means the MCU is shorted. If the MCU is shorted, there's nothing I can do with this other than replace the MCU. So let's remove the transistor and go from there. This is our guy. So what we're gonna do first, let's remove some conformal coating. We're gonna use IPA and a toothbrush. It appears that I'm out of paper towels. That's not good. It's not ideal, but that's fine. I've been using way too many of them anyways. Then let's dispense some Omega 559 flux, all natural, no harsh chemicals, no nothing, just pure organic rosin. Now close it. It doesn't seal. This needle doesn't necessarily seal the flux, so it might the needle might clog up a little bit when you don't use it for a while. Then let's put some leaded solder on it. We are at 374. That should do it. Let's get some nice leaded solder on it so it's easier to remove. And let's grab a little bit of wick and let's get rid of all that solder. Then let's blow some hot air and push the transistor out. Okay, and now the moment of truth. So let's first check the transistor and let's pray that it is shorted between the base and emitter. If it's not, yeah, we got 3K, yeah. So we have a shorted MCU. That's the worst thing that can happen. But we need to confirm that, because we could call it, you know, yeah. Whoa, now it's like completely zero, right? But again, we need to confirm. We could call it, you know, the shorted MCU, but we need to let it cool down, inject a few volts. Actually, I'm gonna inject like 0.8 volt. We don't need much more than that. And yeah, and see what's getting hot. But it's most likely MCU. The only hope at this point is that perhaps it's a shorted cap and we can just replace the cap. But most likely no. Most likely it's the MCU issue. Okay, the ECM is cold. Wires are soldered on. Let's inject 0.8 volts and see what we can see. Now it's still a little hot over here from soldering because I just soldered on the wire, but this side is cold. So well, it looks like it's the resistor that is heating up. Let's put the macro lens on it and see closer. But that doesn't mean the resistor is bad, of course. Yeah, it's heating up nicely over here. Which one? Oh, maybe it's not a resistor. No, it is not a resistor. Beautiful. So it's either a diode or a transistor. It looks like the marking is Q9, so it's a transistor. That is a good news. Okay, which is perfect, because so here's how it works. The big transistor is controlled by a little transistor, which is this one, Q9, this little guy over here. And this is what is shorted. That's an excellent news, because that means MCU should be fine. Yeah, we got zero, pretty much 300, 400 milliamps here, and open here, and open here. I mean, still not ideal, because it's between the base and emitter, or is it between the base and the collector? Well, first let's remove this transistor, and let's see what this transistor is and what kind of replacement we can find for it. I'm blowing right next to the cup, but that's fine. It doesn't require much heat. Then let's clean it up a bit, like so, and there. And we're gonna put fresh new solder on it, but first let's see what this transistor is and find a replacement. This is relatively old. I could just go for the other one that is also marked BR and just not even care what this transistor is. But I mainly have Subarus in the shop, so most likely they're not going to be marked the same. It's going to be slightly different. So I need to find out what this transistor is and just find a replacement. Okay, the marking is a little bit ambiguous, but the ambiguity is between essentially, well, a diode or Zener diode, which we know this is not, just looking at the circuit, right? This is definitely base, right? So this will be emitter, and this will be the collector. Let's check here. So what is this? Is this ground? It is. So emitter is sitting on the ground. We have base here, and the collector is going to the transistor, which means this would have to be a PNP transistor. So we have NPN transistor controlling PNP transistor. It's pretty common, but I was expecting, since emitter is sitting on the ground, not the collector, I would expect it to be NPN. Because in this case, it doesn't really matter whether it's a top transistor or bottom transistor. We know it's a bottom, right? Because the emitter is sitting on the ground. So it's definitely bottom, so the load is connected to the collector, and that's usually how it works. But for that to work, so for this transistor over here to be controlling our NPN transistor, this would have to be connected to the, oh, okay, right. So there are two ways of doing this. So either we're actively controlling the base, because with bipolar transistors, the base is going to consume some power, right? That's why you can't directly control a bipolar transistor directly from the MCU. You can control MOSFET that way, because MOSFET is not going to be taking any power. The gate will either charge or discharge. You still use transistors for that purpose, but you can control it with when there's open collector on the MCU. You can control it directly. That's not a problem. But with bipolar transistors, no, because the current flowing between the collector and emitter is going to be proportional to the current flowing between the base and emitter. So these kind of transistors, they don't control voltage, they control current. So normally you would do it in a way that, because you can do it with just one transistor for bipolars. With MOSFET you need two transistors, one to charge the gate and one to discharge the gate. But in this case, we just want to push some current to the base of the transistor, or to close it, we just stop the current flow, and the current will stop flowing between a collector and emitter. So you can do it in two ways. You can either use this little transistor and connect whatever voltage to the collector and emitter to the base of the big transistor. And that's how you control it. Or you can just constantly push current to the base of the transistor, so it's always open essentially. And this transistor just pulls, which actually makes sense over here. So this transistor would just pull the base of the transistor to ground, essentially closing it, right? So it's always open until the MCU closes it. So that would make sense over here, because our emitter is sitting on the ground, and our collector is connected to the base of the transistor. Let's confirm that. Looks like we're doing it through 47 ohm. Is it 47 or 470 or 4.7 ohm? Let's do resistance, and let's check the resistance here. We got 0.47, so we have 0.47k, right? So we have 470 ohms. Yeah, 47 and 10. So 470 ohms and 470 ohms going to, what is this? This is most likely power rail. So we should have between here and the base of the transistor, we should have 470 ohms. And we have nothing. Nothing, meaning it's shorted to the base. Looks like it's going to this via over here, and somehow on the other side it's probably going to this via over here. But it's also looks like so it's pulled up by 470 ohms, so that would confirm. So between here and the base we should have 470 ohms. Yeah. So it's pulled up by 470 ohms, so it's always open. If this is NPN, so how do we know if it's NPN or PNP? So first let's check this one. If it's NPN, if we get a diode and we test it in forward, so between the base and emitter, that's basically a diode. That will always show up as a diode on NPN. So if this shows us roughly 0.6, it shows us 0.65. So this is definitely NPN, right? And now let's do the same with the big transistor. So if this is PNP, then we know that that's how we open it, right? Because we want to pull the gate to, or the base to ground to open it, right? So again, between the base and emitter, we have 0.57. So this is NPN. And we also have 0.57 in between the collector, because there might be a diode. But the diode should be between the collector and emitter in reverse. Yeah. So there is a diode between the collector and emitter, right? And we have in forward 0.56. It's a little low, but this is power transistor. Now in reverse, it is open, and this one is 1 volt between emitter and base. So I'm not sure actually. I'm actually not sure. This could be both. It would definitely make sense if this is a PNP, because that's how you drive PNP transistors, right? With NPN, essentially shorting a base to ground to open it, and it is always pulled up to keep it closed, and that would definitely make sense. But in this case, well, let's see if we can identify this transistor. Okay, a few minutes later, well, actually like an hour of measuring and thinking and searching. All right, based on the markings, this is definitely an NPN transistor. based on my experience on ECMs, these are always NPN transistors, and they are controlled in a fashion where the base is always pulled up, so the transistor is always open, and the MCU closes it. So in case of a short, like we have over here, in case of a short of the control transistor, that little body, the transistor is permanently closed, right? But if you want to check it with measurements, then base to collector is 0.54, which is correct. Base to emitter 0.57 is fine, but collector to base should be open, and it is open, and collector to base or emitter to base should be open. It is not open. And emitter to collector, if there is a internal diode, and this one doesn't seem to have internal diode, but even if it did, 0.45 is a little low, and collector emitter should be closed, right? So let's consider another transistor. This is C5293. These are used in 2005, 6, 7 Subaru, Outbacks, Imprezas, and stuff, 4 in injector. Now these do have internal diode. We have 0.55 base collector, and base emitter we have 0.55, right? It should be the same measurement. On the other one we have different measurements. Then in reverse we should be open here, and we should be open here, which we're not on the other one. And we have 0.4482 in reverse over here, which actually looks like it's the same, and open collector emitter. But on this one we do know that we have a diode. On this one it shouldn't have a diode, although I don't see the diode outside the circuit. But this one is 40 volts, this one is this one's 60 volts, this one is 400 volts. But more or less it looks like they behave the same. So I would say that this transistor is okay, because it measures pretty much the same as this one, almost the same. But it could be leaking, there could be some issues with it. So we're gonna replace it with this one just to be sure, because we don't want the ECM back. So the only problem now is to find the replacement for the little transistor. So first I am going to resolder the big transistor. So let's remove this, let's remove the wire. Let's do some wicking. Look how well it soaks. See how well it travels. That's both relatively good wick and good flux. There. Now let's put it in circuit. Okay, 2000 Outback, 99 2000, or no, that's 2000 2001 Outback. To the rescue. So we have F3 and L7. F3 is a PNP, L7 is an NPN, and we can confirm. So this will be the base. So base to emitter we got 0.6, base to collector we got 0.6. In reverse here we have 0.6. Well, right now we're in the circuit, so no. Emitter to base, technically it should be open, but we got 2.2 volts, so it's because it's in circuit. So it will be open once we desolder it. And the same with collector to base in reverse. It should be open, but it's 2.4 because it's in the circuit. So let's grab it and let's test it outside the circuit. It's the same size. That's what the same size and same pinout. That's what the issue here was. So this will be easier. I could find, yeah, pretty much any NPN transistor over here would be good. Why is it taking so long? Oh, it's probably glued. Yeah, it's glued. They glued them I recently learned that from a comment from you guys, that some of these are glued because they solder it on the other side, so they don't fall off. They are first glued, then they are soldered. Beautiful L7. And now again, let's see the reverse between the gates. So we want to see open over here, and we see open. Yeah, and we should see open over here. Yep. Okay, and in forward, let's check forward again. So the base to emitter. Oh, come on, it's not that easy, but we got 0.6. Yeah, it's not that easy to catch it, but we got 0.6 and 0.6 base to collector there. Okay, so that's our replacement. So let's drop it in the ECM and we should be done. Okay, now it's gonna be a hybrid Mazda and Subaru, both Asian, so they should be fine, right? No, it's really, you know, these transistors, they are swappable, because especially for injectors, you know, the output stage might require a little more thoughts, right, a little more matching, but for the control transistor, it really is not that important. Not that important meaning the actual parameters, properties of the transistor are not that important. It just needs to work basically like a switch. And since we're replacing it from other ECMs, they serve the exact same purpose, just on the different car. But it's the exact same principle. Can we just... and one last collector, come on, there. Alright, that should work. Alright, it seems, so I replaced the handle, the whole handle, and it seems better. So I'm not sure if this was a handle problem or the soldering iron problem. That's why it's good to have replacement handles on hand, because that's easy to confirm. And my scope keeps restarting. That's another problem. I'm not sure what it is, probably power problem, but we'll see. Okay, so let's give it a closer look. I think it looks good, but just to be on a safe side, because I really don't want this to come back again with some other issue, you know, or especially if it's an issue that I messed up, basically, you know, messed up soldering or something like that. So let's reflow it a little bit with flux. That's gonna ensure good connection. This is omega 559 with citric acid, so it is slightly aggressive. So even for corroded pins, corroded pads and stuff like that, it'll still work. Oh, I praised it too quickly. Yeah, too soon. Yeah, yep, it's behaving the same way. So I don't know what's going on here. I think I need a new iron, and that's pretty much it. It's been years this iron has been serving me, so you know, I'm not gonna get mad if it breaks, because it definitely paid for itself many times over. And there it is. So now let's measure the gates again, or the bases. So now on this one we want 0.32, on this one we want 0.26. Yeah, it's the same. I was expecting a little different reading actually on this one, because before we were checking with no control transistor, no driving transistor in circuit. Now we have, now we do have it, so I was expecting slightly different reading, but that's fine. All right, now the ignition. I mean, they said that the ignition was weak, not that it was not present, so we don't expect any shorts or anything. But why would it be weak? And how do they actually measure that? Okay, I'm doing the reverse. Base emitter 0.7, 1.3, 0.7, 0.7. Why is this one 1.3? It's a little suspicious. That could explain weak ignition, but why? Let's let me mark the 0.7, and this one is 1.3. So let's mark this guy here, and let's check outside the circuit. If it's 1.3 outside the circuit, we're just gonna replace this guy. Let's just desolder it like this. There's plenty of conformal coating on it. That's the main issue here. It's difficult to clean because of that, especially once it mixes with flux and stuff. It's a little pain to clean it, and especially since it's old conformal coating and the new conformal coating that I put on. Okay, and the transistor is E1F3P. I have never seen this one before, so that's the first for me. So now let's see what we can find out about it. Actually, before we do, because if it tests fine outside the circuit, we're good. So we don't need to do anything with it. We just need to place it back. So now it's 2.7 base emitter, and we have 0.4 base collector, which is not good. Emitter collector looks like fine. Collector emitter is open, that's fine. And collector base and emitter base, it does not look good, especially base. Yeah, so base emitter we have 2.7, and base collector we have 0.46. That is not great. Let's confirm the circuit again, if I'm getting the right, but yeah, looks like, because it might have different pinout, which still doesn't explain, even if it has different pinout, still doesn't explain why the other ones are testing okay and this one is not. Let's check again over here. Yeah, the pinout might be different actually, because we have a control transistor over here. Yeah, so the base collector emitter most likely, right? The base is going here somewhere, probably to the MCU or somewhere. So that is controlling base collector. So emitter. Okay, so so this is the collector. Emitter goes to the base of this one. That's weird. I mean, so this would be base. So one of these is collector emitter, and oh, never mind. We have marking on the board. So Q103 emitter is here, and emitter is here. Okay. So let's do the base to emitter. So base to emitter. Yeah, we have 1.3. That's not good. And we have 1.3 on base collector. So that doesn't look good. Let's flip it. So we have bases now. Bases are on the left, and that's how I was measuring it, because I was just looking at the. So I knew this would be emitters because they're all connected. They're all on the ground, right? So I don't even need the actual pinout. And usually the base is never in the middle. I mean, usually never. But also we can see the small trace going over here, right? And this one we don't see the trace because it's on the other side, but we saw it before. So base collector emitter. So it's just kind of in reverse, right? So if you want to replace it with a different transistor that has the regular pinout where you go from the left, base collector emitter, then you just have to flip it basically, and that's how we do it. So yeah, base to emitter now without the transistor is open, base to collector it's open, right? So this one, base to emitter, it's 0.7, base to emitter 0.7, This is, we don't know what it is, but looks like the same thing, base to emitter 0.7. And this one, this transistor is showing much higher. So I conclude that this transistor is shot. So now we have to find a replacement again. This ECM is going to kick my butt. All right, so here's the issue that we have. This transistor is not available. I mean, we'll get to that in a second. First, let me show you what this transistor is. So the transistor in question is a compound transistor, on-chip resistor, NPN silicon epitaxial transistor for mid-speed switching. So it's a switching transistor, right? With high HFE. We have on-chip Zener diode for surge voltage absorption. Now the reason for that is because we're driving inductive load, right? This is for the coils. On-chip bias resistor, 2.2 and 10K. Now this we could technically recreate outside the circuit. It should be relatively easy. I mean, it would be a little hacky because we have to desolder or remove the base and solder on two resistors, 2.2 and 10K. Low power consumption, that doesn't really matter that much. It's perfectly fine. I mean, it could, depending how the driving circuit is done, but from what I can see, we're driving with a regular NPN transistor. So yeah, it shouldn't be a big issue. And we have on-chip damper diode for reverse cable. Now this is a 60 volt transistor. A collector current is just 2, plus minus 2 amps. That seems a little low. And we have plus minus 3 amps in poles. So this is likely what we're... yeah, the coil doesn't really need that much current because we're driving it at 12 volts or 14 volts, what have you. So yeah, it's not a lot of current, but it is a little low. I would like to see a little higher for this purpose. I would like to see it a little higher, but we have that Zener diode to protect it from the coils, from the kickback from the coils. Emitter to base is 15 volts. I would say that's a little too close. I would like to see that at like 25 volts for this purpose. Our turn on time is 0.4 microsecond and fall time is 0.5 microseconds. This is important. In this case, this is the most important aspect. So with, as I said, with injectors, it's not that important, right? So few microseconds of a difference, that's not going to make much of a difference. But for ignition, it's going to make a lot of difference. So if our replacement transistor has, say, 5 microseconds instead of 0.4, that's going to make a big difference because the ignition is going to be delayed. And that's, for the engines, that's relatively important. And we have characteristics over here, which, yeah, we could match. The characteristics we could match, but it's going to be hard to match this. And actually, this we could match, but we need to match it along with the bias resistors and the Zener diode. So that's going to be difficult. So the best solution here is to get the exact replacement. And the only place where I found it is AliExpress. It's not very expensive, but it's going to be 2 weeks before it's delivered. And the problem here is that the customer has a car at the mechanic, and the mechanic is charging her for every day of storing that vehicle over there. So if I now come back to her and say that we need 2 weeks to source the transistor, I don't think she's going to be happy. So at this point, we have to stop and we have to publish the video and we have to ask the customer what she wants to do with this. I would be very reluctant to replace it with just a transistor that I find that is kind of the same. because this is for ignition. There's very little wiggle room on ignition circuit. That's why on Subaru, these are all dedicated chips. Even on the older ones, yeah, I can get the ignition transistor from Subaru, and we can see if that works. Or I can source the transistor, the exact replacement. Now, important to understand is that it's not only the transistor. So, you might think that since on Subaru the transistor works, and then it should also work on Mazda, right? Because it's driving pretty much the same coils. True, but the difference is how they are controlled. The driving circuit over here is going to be slightly different. They all work on essentially the same voltage, because the same battery, same ignition, same principle of how the engine works, but driving is different. So I would be very reluctant to replace it with Subaru transistor. But I can, and we can test it out, and maybe it'll work perfectly fine. Maybe I'm just making mountain out of molehill. Could be. But we have to get an okay from the customer. Well, sometimes these are pretty difficult to diagnose, pretty difficult to fix because of that. The parts are no longer available. Typically on these, what happens is just it corrodes. You have to fix the corrosion, restore traces, and that's usually what we do. Now the mechanic advised the customer that he's got a guy that does rebuilds of these for $175. I'm not sure if anyone would like to go through all this for $175. And my price is also pretty affordable because it's $200, right? So it's just a matter of, or difference of $25, not that much. But sometimes it takes hours to diagnose everything and to actually fix everything. And this is one of those cases. So let's put the transistor aside. Other than this weak ignition, because the transistor technically works, but that's why the ignition is weak. The junction is just degraded. That's why we're reading twice as much voltage drop than we should. This is kind of typical for bipolar transistors. That's how they degrade. It's also the same for the diodes. If the diode, instead of reading 0.6 reads 1.5, then that's the same issue. The junction is just degraded, and especially on ignition, that happens. So, well, so far, or at the moment, we're not going to have an answer, and I will publish another video replacing it with perhaps Subaru transistor, and we'll see. But for now, this is it. Thank you guys very much for watching. I hope you found this useful, and I shall see you guys in the next one.